Hello. Today we are doing a practical activity to apply our knowledge on the topic of vectors in physics. Let's consider the following example. Vector A with a magnitude of 27 meters is directed at an angle of 30th degree above the positive direction of the x-axis. Vector B of magnitude 35 meters is directed at an angle of 55 degrees below the positive direction of the x-axis. Draw vectors A, B, draw the sum of these vectors and determine the length of this sum and its direction. Let's write down the conditions of the problem. We know that the magnitude of vector A is 27 meters and it is directed at an angle theta, denote this angle, to the x-axis 32 degrees. The length of vector B is 35 meters and it is directed at an angle of beta equal to 55 degrees. Question. We'll need to draw the vectors A, B, show them in the figure, then show the sum of these vectors in the figure. And determine the length, and let's introduce some angle, let it be gamma, which will describe the position of this vector in relation to this x-axis. Let's start with a drawing. That is, we have to initially show the x-axis about which we're going to draw the corresponding vectors. We do not say how they are specifically located in space, so we can combine these vectors in one point, that is, make their common origin. And it is very important here, of course, to understand how they are located in relation to the x-axis. And here, by the condition of the problem, it was said that vector A is located in such a way that it lies above the given axis x. That is, it has an angle theta, which is above this axis. That's vector A. And the length of this vector is 27 meters. We pay attention to the fact that the length of vector B is 35 meters. This we must also display in the figure. That is, when vector B is drawn at an angle of 55 degrees below the x-axis, we draw it approximately in this way. And the length of this vector B, of course, we also try to depict in accordance with the value of the parameter of this vector. So, we have two vectors. We have plotted them in the figure. Denote the second angle BT, which we will also use in solving this problem. And now we need to plot their sum, the sum of vectors A and B. Well, in this case, we see that this figure is ready to solve the problem through the parallelogram rule, i.e., the vectors have a common origin. So let's build this figure to a parallelogram. For this, we need to measure the corresponding equal segments and connect them to each other. So, schematically, we receive this figure in this way, and we draw the diagonal of the parallelogram, which will show us the sum of vectors of vector C. This diagonal of the parallelogram, well, and accordingly the sum of vectors is located under the gamma angle, which we will define later to the x-axis, respectively has its length. And now the question arises how to determine the length of the final vector C. To do this, you and I must again remember that each vector and the components of the sum vector and the sum itself, they are decomposed into components. That is, vector A has components AX and AY. Vector B has components BX and BY, and vector C, of course, also has its components CX and CY. CY. If we have vector C was obtained as a result of the sum of vectors A and B, then the component of vector C, Cx, will also be determined by the sum of the components of vector A and B along the x-axis. In the same way, we work with the components on the y-axis. Therefore, for simplicity, let's write down the expression that will allow us to solve this problem through the components of these vectors. So the first expression looks like this. And now in order to determine the components of the vector Ix and Bc, you and I will recall how they work through the angle that you and I know. And this angle is the vector itself with the x-axis. X, let me remind you, is the product of the value of vector A of its modulus by the cosine of the angle θ. BC is the product of the modulus of vector B by the cosine of angle V. Therefore, immediately let's write down what the component of the vector C will be on this axis. So, the value of vector A is 27 meters multiplied by the cosine of 32 degrees. The sum of vector B and another vector is equal to 35 meters multiplied by the cosine of 55 degrees. Given that we have angles here that are not tabular, of course we get a not quite even answer. Approximately 43 meters will give us the component Cx. Similarly, we work with the component Sj. That is, in this case, we can build an axis perpendicular to the x-axis, it is the y-axis, and consider the components along this axis. That is, the Sj component will be Aj plus. By. And let's calculate their values. So, Ay is A multiplied by the sine of the tetraangle and By. Here we pay attention to the fact that Byu, i.e., the vector itself, is inclined below the x-axis, and in this case it goes to the negative region of the y-axis, so its component will go with the minus sign. Minus b by the sine of the angle b. Therefore, in order to calculate the y-axis component of vector C, we apply the following formula. Vector A multiplied by the sine of 32 degrees and then subtracting 35 from the result. Times the sinus of 55 degrees. In this case, I'm subtracting one component from the other until we know which one is greater, which one is less. Just subtract and look at the answer sign. By doing the appropriate calculations, you and I arrive at an answer of approximately minus 14 meters. What does that tell us? That the component of vector B along the y-axis is greater than the component of vector A. And that's why actually we have vector B outweighed vector A by its value, and vector C is already looking below the x-axis, which is basically confirmed by our figure. We have found the components of vector C, i.e. we know both Cx and Cy. Now it remains to calculate the magnitude of this vector. Let me remind you of the equation that allows us to do this. That is, knowing both components, we can easily make these calculations. The first component is 43 meters. And the second component here, we can basically leave the minus sign. It's not crucial, because in any case, we consider the modulus of this vector, and the sign of this component is not important to us. After doing our calculations, we arrive at an approximate value of roughly 45 meters. Such length will have a vector C, and it remains only to calculate its angle, the angle at which this vector will be inclined in relation to the x-axis. In order to determine the angle of theta, we can use the following construction. Let's draw from the end of vector C perpendicular to the x-axis. And you and I get a right-angled triangle in which the hypotenuse is a vector C. There is a catheter that is located along the y-axis. This is how we understand the component along the y-axis. And there is a catheter that is located along the x-axis. This is its component along the x-axis. In order to determine the angle of inclination, we can now use any function that you and I know, that is, connecting the angle and some sides of the triangle. Suppose we can find this angle without determining the magnitude of the vector C itself. That is by using, for example, the tangent of this angle. Recall that the tangent is the ratio of the opposing cathetus to the adjoining one. In this case, the opposing cathetus is the component on the y-axis. The adjoining one is the x component. So the ratio of these two components gives us the answer for the tangent of this angle. Component on the y-axis we take in 14 with a plus sign, because we care about the modulus of this angle. If you put here a minus sign, just the angle will be negative and it will show that the vector lies below the x-axis. But this we have already determined. And the value of the x-axis component is 43 meters. Thus we have obtained the value of the tangent of this angle, and of course the angle itself will then be defined as the arctangent of this ratio. Which is approximately 18 and 4 degrees. We have successfully coped, put on the problem, determined all the necessary values, coped with finding the value of the vector c, its direction in relation to the x-axis, plotted it in the figure. So this example shows how to work with vectors, how to work with their sum, how to calculate the components of the corresponding vectors, and I am sure it will all be useful to us further in practice. See you soon. Goodbye.